Hello and welcome! This is a video tutorial on how to use the REMCU Lib on Unix-like operating systems like macOS and Ubuntu. Now we're going to show how easily it is to control microcontrollers' peripherals on a common MCU development board from a customary personal computer. However, we will not be developing a firmware and communication protocol for command transmission. We will just be working with the chip's peripherals from our C++ programs and Python scripts, as if these peripherals were part of your computer. To interact with a microcontroller hardware from our personal computer, we're going to utilize the driver functions of standard peripheral library of ST Microelectronics Company. It is a vendor software development kit provided by the company for writing firmware. You can see detailed information about the standard peripheral library on st.com. There is documentation and samples which are useful for working with STM32 chips. We will call these driver functions from our user space applications, just like we call them for hardware operations from firmware code. The REMCU Lib makes it all possible. The library translates a local driver function call on our personal computers to a remote call of the same driver function on the chip using a communication or debug interface. You can see a description of the REMCU Lib and other tutorials on the website remotemcu.com. In this tutorial, we're going to build and run the examples on macOS. For Ubuntu and other Linux OS, there are the same sequences of actions. We're going to use a STM32F discovery board in this tutorial. All examples are designed to work with this device, but they can be adapted to run on other STM32 boards without any difficulty. You can download them from the GitHub repository. The first app is an acceleration graph maker which captures data from the board's MEMS sensor. Another app is a CAN bus analyzer. And the third example is a Jupyter Notebook script with C++ code which works with the GPIO, PWM-ADC, DAC, and DMA models of microcontrollers. First, let's download the GitHub repository and unpack the archive. You need the REMCU library to build the examples. It can be found on the Downloads page of the remotemcu.com website. Type STM32F4 Discovery in the MCU name field. Then select Standard Peripheral Library in version 1.1.0. Download the archive of the macOS version and extract it to the first example directory. Open the Excel graph project using the Qt Creator IDE. If you don't have a Qt Creator, install it before that. In order to build this example, you're going to be required to install the Qt Charts component. Alright, now let's build and run the application. The application started. We have downloaded the community version of the REMCU library. This version works only with OpenOCD or GDB server for connecting to a microcontroller. The discovery board contains a ST-Link debugger which works with the OpenOCD utility. You can download a pre-built OpenOCD package from the MCU Eclipse repository. Download the archive now and extract it. Connect the development board to your computer and run the OpenOCD with the required options. Alright, now the REMCU library can connect to the remote STM microcontroller and interact with it. Let's go ahead and press the Connect button. The program will start capturing the acceleration data and build the charts. Now, if you run into any trouble while trying to launch these examples, please see the troubleshooting page on our website or issue page on the GitHub repository. I would like to note that we didn't load any specific firmware into the microcontroller. Our program just works directly with the I2C peripheral block of the STM, using the driver functions of the standard peripheral library. Interfacing code with Onboard Accelerometer have been taken from the MEMS sample of that library. The REMCU Lib translates all local driver function calls to remote calls of the same driver functions on the chip using a debug interface. Typically, to communicate with an I2C device, one would use a USB to I2C converter. In this case, the STM chip acts as that converter. But unlike a highly specialized converter, a microcontroller has potential and a rich number of peripherals. Now let's test another communication protocol of STM32. The second example covers a CAN bus peripheral. The video REMCU Lib Windows tutorial has detailed information about how these examples work. You can easily repeat it on your Mac or Linux OS. One very important thing to take into account about the REMCU Lib is that it's a simple dynamic library. It does not depend on the Qt frameworks or the Qt creator. You can add the REMCU library to other IDEs and frameworks, and even use it with a C++ interpreter. For instance, take a Cling C++ interpreter. The interpreter lets us run and execute C or C++ code on the go. In this way, you could call the functions of a driver directly and control MCU or SoC in real time. With this tool, you can also easily conduct amazing experiments on chips, peripherals, and microcontroller-based devices. It saves a lot of time that is usually spent on the development of experimental firmware. The interactive work with the chip's peripherals helps us discover new hardware blocks quicker. Let's test the library with the Cling C++ interpreter in the Jupyter Notebook IDE. Now this is going to be much easier with the Anaconda environment. Let's go ahead and download an installation package for Anaconda distribution version 2 or 3 from anaconda.com and install it. Then, run the Anaconda Navigator and install the Zeus Cling package. And Xplot package. And also Xwidgets package. We have prepared a sample script for experiments with hardware. It's going to be in the Jupyter Notebook folder. Copy the REMCU library to this folder. Connect the board to the laptop and run the OpenOCD utility with the required options. Now run the Jupyter Notebook and open the sample script file. Let's have a closer look at these functions. The first row loads the REMCU library. The second row adds the include directory, including the header file. Now take note, the REMCU.h header must always be included before any device driver header files. The next step is connecting to the debug server. Upon a successful connection, the function returns the true value. Otherwise, it will return false. The next step is resetting the chip. If no error occurs, the function returns true. That's all. The configuration of the REMCU library is now done. Now you can call the functions of the standard peripheral library and manage chips peripherals. Okay, the system init function sets up the microcontroller clock system. You can see the clock system configurations in the system STM32 F4.c file. Now let's play a bit with the LEDs on the board. This code was taken from the I/O toggle sample of standard peripheral library. It configures GPIO as an output port. Let's flash on the LED. Okay, now flash them off. Well, if it didn't happen, you can use the utility functions to detect errors. The REMCU getErrorCount function returns the number of errors that occurred after connection. The REMCU is connected function indicates the status of the current debug server connection. Some of the debug adapters can have hardware problems. The REMCU debugger test function enables us to detect such adapters. The function returns a null pointer if the test is successful. Working with GPIO is always interesting, of course, but let's try something harder. Why don't we try testing the timer module? This code is guided by the PWM output sample. Set PWM mode for timer 4. Now you can control the duty cycle and adjust the brightness of the onboard LEDs. The Jupyter Notebooks is not just a static document. It has great dashboards perfect for exploring and visualizing data. Let's go ahead and use it. Create 2 controllers for changing the LED brightness. It's that easy. The next example takes ADC data from the microcontroller and visualizes it into this notebook in real time. The sample rate of ADC is 2 megasamples per second. With this high rate, moving samples one at a time is inefficient, and as well as it leading to gaps in data collection. The correct technique for handling large amounts of data at high sampling speeds is to use direct memory access, or DMA. The DMA enables buffering received and transmitted data from the peripherals to the microcontroller memory. And the REMCU library can load and store it to the memory. This code was practically taken directly from the ADC3 DMA sample of standard peripheral library. Configure ADC and DMA to work together. To get the ADC value, start conversion and you can read the buffered values from the chip's memory. The load from mem function loads data from the remote microcontroller memory to the local array. Alright, now let's run the code. If no error occurs, the function returns true. Now print the array of ADC values. Let's visualize it. Connect a signal generator to PC2 pin, and then run the snippet. The continuous stream of ADC data will be visible on this canvas on the interval of 52 microseconds. The Sine-Wave Sketch is yet another application of DMA. So with its help, we can generate a seamless sine signal. This code is based on the DAC signals generation example of the standard peripheral library. First, we should upload this array of a sinus signal to the microcontroller memory. The store to mem function will do this for us. If no error occurs, the function returns the true value. Note that the community version of the REMCU library has a 32-byte limit on the memory operation. Therefore, if you need to copy a lot of data, you can do it in parts. Let's plug a probe to the PA4 pin and run configuration on DAC and DMA. Amazing! The DAC is playing the uploaded array. You can remotely change the MCU's memory using the REMCU function, and the DAC will play the modified content. Let's talk about some other useful functions. The getVersion function returns a string with the library version, and the last function disconnects from the debug server. All the code in this page is just a simple C code that you can use in your C and C++ projects. It is also possible to use the REMCU Lib with high-level languages like Python, Java, C#, and others. To make working with them less troublesome, we provide language wrappers. With these wrappers, it becomes easy to work with hardware as it is using C or C++. The video tutorial REMCU Lib Windows demonstration shows an example of work with Python that can easily repeat it on your Mac or Linux OS. On top of that, The REMCU project provides not only API of standard peripheral library for working with STM chip, it can implement other interfaces like HAL, Mbed, Arduino, and others. And furthermore, there are versions of REMCU library for other chips, including 8-bit, 16-bit, 32-bit microcontrollers, and 64-bit systems on a chip. In case you've not found a community version of REMCU for a certain library or chip, just leave a message on our website or write an email. Thank you very much for your attention. If you have any questions on these examples, you can always raise an issue in the GitHub repository, or send us an email with your questions about the REMCU library.